thanks. Welcome, everybody. So a little bit about Q42 first. We're here in The Hague. Q42 also has an office in Amsterdam. And we are in total about 85 nerds who work on websites, backends, mobile applications for both Android and iOS. We do a lot of native mobile development, but also some React Native, some Flutter development, etc. If you want to know more about Q42, you can find us at q42.com. On to my talk. So I'm going to tell you some things today about frameworks and libraries on Apple platforms. So why did I come up with this topic? So last year I was doing a project for a client at Q42. And this client was a building construction firm. And they have all these 3D models of buildings. And they wanted to visualize them in augmented reality on the iPad and iPhone, basically. So they're working in this architectural software called Autodesk Revit. And it spits out a certain file format. It can export these building models to something called an IFC file. And that's what I needed to open in my app and display it in ARKit, basically, and in SceneKit. I could do that myself, so parse that file format, but it was complicated, and I needed some C++ libraries. There already existed a bunch of open source libraries for working with this file format and for working with 3D geometries, etc. So I wanted to use them, but they were cross-platform libraries. They would run on macOS, on Windows, on Linux, but not on iOS specifically. And hence I needed to learn a bunch of things to get it up and running. For this all still context for what I'm working up to, but we have this IFC file that the architects give us. The app needs to open it and convert it into some form of 3D geometry. And then we load it into SceneKit and ARKit. And this part is where the libraries come in. So I found something called IFC++ and Open Cascade, which did just what I needed. But compiling these on my poor Intel Mac took like 30 minutes. So I needed to package them up somehow into binaries so I could ship them with my app, because I had to pre-compile them, because waiting 30 minutes every time you need to do a clean build is no fun at all. And the app architecture I ended up with looked like this. So we have our app, which is written in Swift, and it uses a Swift package that I wrote myself called IFCKit. I dubbed it that. And that needed to interface with the C++ libraries. As you can see, the libraries, they are written in C++, and my Swift package is written in something called Objective-C++. So that's actually Objective-C that can call into C++ code. This was written last year. Just now at WWDC 23, Apple announced C++ interoperability for Swift. But unfortunately, I didn't have that last year. So hence, I needed to drop down to Objective-C. So 4 topics that I'm going to take you through to get from nothing to a finished app, basically. First, we're going to talk a bit about static and dynamic libraries. I didn't know the difference between these, so I dove into it and I'm going to explain it. Then mergeable libraries, which is something Apple just introduced this WWDC. Multi-architecture frameworks using XC frameworks, and a bit about the Swift Package Manager, because the Swift Package Manager can actually do more than you might think. So, static and dynamic libraries. If you ever created a custom library in Xcode, you get these choices, framework or static library. And I didn't actually really know what that meant under the hood. So the framework option is what you would call a dynamic library, and the static libraries is the static library. And I'm going to start with those first. What is it? So static libraries, they've been around since the 70s on Unix. So you have your C file. If you're writing in C, then it goes through a C compiler, this CC thing. CC is an alias on your operating system, usually for your C compiler. So if you type that in on your Mac, then it will give you Clang, which is Apple's C compiler. And in this case, it just spits out a program. That's how it started. You have your executable. It's a binary, and it runs. What happens if you have multiple C files that you want to combine into one final program. So for that, object files became a thing. So notice how prog over there turns into prog.o, and the other.c turns into other.o. So an object file is basically a compiled file that contains your symbols, so your functions essentially, and that can then, it's an intermediate product that can be combined into a final binary. And for that, the linker was introduced, which is called LD, a link editor, and it merges those two object files into your final program. And this happens the same way for Swift files. Swift files also get compiled by the Swift compiler, the object file comes out, and it gets combined by the linker. And we can demonstrate this real quick in Xcode. So I have my Hello World application here. I created a Swift UI app, and I added a little dynamic framework called My App Core. And when I go here in Xcode, let's see if I can zoom in, to the report navigator, every time you build or clean your project, something shows up here. So in this case, if I build, my build log shows up. You can see all the tests that Xcode does under the hood, which is actually really useful in a lot of scenarios if you don't know, if you want to know what's going on. In my library, I have a file called math.swift, and it has this huge command here that shows what it kind of does. And what I care about here is the output of the compile phase for this Swift file. So here it outputs a math.o file. And when I go to my terminal, I'll magnify this, I can check what kind of file this is. And it says it's a mag.o object. So mag.o is the format that Apple, that macOS and iOS use for such binary files. That's because the research kernel that macOS was eventually based upon is called mag. And using something called otool, we can actually view the contents of this. Oh, excuse me. So basically it says, please dump this object for me and give me the text section. And the text section, that means basically the binary instructions in this case. It's a confusing name. It has some weird name here, as you can see. And this is what you call the mangled Swift name of the function. And underneath are the assembly instructions in ARM64 for that. And we can actually check what the actual name is by running swift demangle, putting the name in there. Let's see if I copy this. And it says myappcore.square, which takes an int and returns an int. And that's exactly what's actually in here in my math function, math file. So yeah, that tells you for C and for Swift, either way it gets compiled, an object file comes out, and the linker merges that. We can see the linker also here in the end. So first all of my source files get compiled, and then the linker goes to work to link it together. So we have this model here, so we have lots of .o files that combine into a program. What if we get a library from a third party with a bunch of files that we want to merge in there? That's what started happening. The people were passing the .o files around, I think, and they wanted a better solution. So then we have a bunch of library functions, and there was a tool, an archiving tool called R, which they used to combine the object files into an archive. And the linker was adapted to read from that archive file directly. And that would then result in your final program. And that's basically it for static linking. The downside of this was that the final program that comes out keeps growing. All the code from the libraries gets merged into one binary. So then it was optimized because the linker knows actually what symbols are used, what functions are used for my program from the library, and can only copy over those functions from the object file. So then the final binary gets smaller again, and this is what's called in Xcode dead code stripping, dead code elimination. So if you have an iOS application, it depends on a static library. Apple always uses this symbol to refer to a static library. Then the linker goes to work and the library gets merged into your app, and there's nothing else. Basically, the binaries are combined. Then came along dynamic libraries in the 90s. Programs were getting more complex, and it was becoming unpractical to merge everything into a single program. It would get too big. So what happened was we put those object files we did earlier into the linker, and we get a dylib out of there. That's what Apple calls a dynamic library. On other platforms like Linux, it's called a shared object file, or DSO. On Windows, it's called a DLL, a dynamic link library. What happens then when we produce our program like this, the linker knows what's available. It produces a program, but the functions that we use from the library, they get encoded into sort of like a promise. So it promises that at runtime the function is going to be there, and it's going to be patched in there, but it refers to the code in the dylib that is actually somewhere else on the disk. It's not included in the binary at all. So when we launch our program now, when we launch our program, a dynamic linker goes to work. It reads the dylib from the disk, and it patches in the code basically into the slots where those promises are. And if you ever had a problem when developing your iOS app where your app crashes on launch and it says unresolved reference, unresolved symbol, that's because the dynamic linker tries to resolve a function, but the library was missing, it wasn't there, wasn't shipped with your app or something. So for the dynamic library scenario, if you make an app with it, this is what it looks like. So your app depends on the library. Apple always uses the yellow toolbox for a dynamic library. And it gets shipped into your app bundle, your IPA file or your .app on macOS, shipped along to the consumer of your software. And as soon as you start up the app, the system loads the libraries. And this is nice because in case of system libraries like SwiftUI or UIKit, the virtual memory system can do its magic. So when an app launches and uses SwiftUI, if there is already a copy of the SwiftUI framework loaded into memory, the system can just reuse that. It doesn't need to make an extra copy in RAM. Then onto mergeable libraries. So this is a concept that was introduced by Apple this year at WWDC. And mergeable libraries, so the static and dynamic libraries, they both have their pros and cons, right? So the static libraries, with that case, if the library changes, you need to recompile your whole application to patch in the new functions. And for a dynamic library, less recompilation is needed. Depending on your use case, you select a static or dynamic library, and mergeable libraries kind of gives you the best of both worlds. So this was just introduced in the new version of Xcode, and when we have a mergeable library, marked it with a star like this, Xcode can basically choose at compile time if it merges that library into your app, or if it treats it as a dynamic library. So the three libraries here, MyAppCore, MyAppUI, and MyAppUtils, they are all mergeable. And SwiftUI is not because it's a system framework. So when I compile my app, these all go into my application. And it still depends on SwiftUI as a dynamic library. So then this is my final app. And this is nice because the dynamic libraries, they introduce a launch cost, a launch overhead to your app. So if you launch your app, DYLD, the dynamic linker, needs to kick in, load all those libraries from disk into your app. And in this case, if it's merged in, it's faster because the app can load straight into memory from disk as one. So for mergeable libraries, they added some options to Xcode. There's the build mergeable library option if you have a library target, framework target. You can turn that on to enable support, and then in your app you turn on create merge binary like this, and Xcode will do the rest for you. I have not had the chance to play with this much in my own apps, As I said, the app that I did all this for was last year, so then this option wasn't available. But yeah, know that this is available now. One other scenario that Apple mentioned is if you have multiple mergeable libraries, another library depends on them, but it itself is not mergeable, then it will work like this. So the 3 dependents will just be merged into this library, myapplet, but because it itself is not marked as mergeable, then it will remain separate as a dynamic library. And these are, just as any dynamic library, distributable as an XC framework, which I will talk about in a minute. And again, the user of the library, so my app that I use it in, decides whether it's merged or not. Onto multi-architecture frameworks, aka the XC frameworks that I mentioned earlier. An XC framework is something introduced a couple of years ago by Apple. Leading up to the Apple Silicon transition, they actually introduced this because we have all these platforms. We have macOS, iOS, tvOS, watchOS, and multiple architectures. In case of the Mac, we had the architecture transition to ARM, and they they basically solved these problems of having lots of copies of the library for each platform and architecture by creating a container format, which is called XC framework. And a single XC framework that contains multiple copies of one static library or dynamic library, but for multiple architectures and platforms. And Apple uses the blue toolbox to refer to that. So we have these yellow platform-specific frameworks, and an XC framework merges them all into one container, which you can easily pass around as a dependency for your apps. And then Xcode will automatically select the right platform and the right CPU architecture that it needs to do the compiling that it does. It looks like this. So an XC framework is literally just a folder with an info.plist file in it. In this case, this is a static library, so you can see the .a file here, like we talked about earlier. And it has a little folder of headers, because it's a Objective-C library. You need to ship headers with it to know what's in there. In case of Swift, it ships a Swift interface file, which is sort of like a header file for Swift, but that's managed for you by Xcode. Dynamic library looks like this. Similarly, we have a folder here for iOS ARM64 and the simulator. We needed that for my project last year because I was still on an Intel Mac, but someone else was on an Apple Silicon Mac. On Intel Mac, you actually have an Intel simulator, so you need that binary. Oh, and this is actually the wrong screenshot, I think, that I put in here. This is also an A file, sorry. So how to build one? If you have your Xcode project, so I made a project for this IFC++ library. We can specify our destinations, so I need it for iOS and for the simulator. And we need to pass these 2 options, most importantly. The skip install means that Xcode will include our build library into the archive. And the build library for distribution, it enables the right optimizations, I think, for the build. And it includes the metadata for the library that Xcode needs to consume later to use it. And then the second step is to convert that Xcode archive into our XC framework. We use this command for that. The Xcode build create XC framework. And we just need to specify our archive path and the name of the framework that's inside, and then our output. And then as a result, we get a folder basically just like this one. That's all well and good, and how do you use it? It's a question.
Yeah. My question is like...
Do we need a mic for the question, by the way?
So my question is, where did you put these commands? Like, did you put them in a make file or just a shell script, or how did you do it?
I made a shell script and I put it on a GitHub Actions workflow in my CI. So basically for the IFC++ library, I forked the library to my own GitHub, and I expanded it with an Xcode project and some CI configuration that uses these commands to build the framework, zip it up, and it uploads it as an artifact. Yeah, and in a minute I'm going to show you how I actually then use it in my project using the Swift Package Manager. So one way to use it, if you have an XC framework, is just drop it into your project. Back in the day, we used to do that. We would check them in, check our framework and drop it in there. And for an XC framework, it works the same. You get again the blue toolbox, and Xcode decides which framework from the container it will use, depending if it's for iOS, macOS, and for which architecture. But the Swift Package Manager actually understands the XC frameworks as well. So Swift Package Manager is, of course, the package manager if you're developing for Apple platforms. We've had CocoaHeads and Carthage for a long time, and then Apple came out with SPM years ago. And it's what I would recommend to use for everything unless you can't. You can put code in your packages, resources, and binaries. So, of course, you can put source code in there, your Swift code. Resources as well, if you need to ship images or localize strings, that actually works in a Swift package. And binaries, which we'll talk about in a minute. Also, it's called the Swift Package Manager, but it supports actually 4 languages, the same 4 that Apple supports in Xcode. Swift, Objective-C, C, and C++. So you can totally make a Swift package that's written in C or in C++, as long as you do not mix Swift in there. You cannot mix Swift with any of the C family languages. You cannot mix them in the same target, if I'm correct. So if you have one package and you have multiple targets, and each target must be the same language. So then, to answer your question, I had my GitHub action create and compile my framework. Then it uploaded it as a GitHub release, and it gives it a URL where the Swift Package Manager can download it. So then in my project, I have my app, my Swift package, and it depends on those 2 libraries that I mentioned. We pass it a URL and a SHA-256 checksum, so that SPM can verify if it's not tampered with. And that's all we have to do, basically. Xcode and the Swift Package Manager will wire it up so that within the package I can import the headers or import the frameworks that I want. And will be included in the shipping app, of course. And that's how we ended up like this at the picture that I had all the way in the beginning. So my app, and it depends on the package, and the package depends on 2 libraries that I can harness all of the power of. That was really great. The source I used for this talk are these WWDC videos. If you want to dive in deeper, I can recommend watching those. And they go way deeper into how the linker works, into how Swift Package Manager works. And that's all I got for you. Are there any questions?
You said it's optional to choose if you want to make it a mergeable library and if you want to merge a library.
Yes.
But what are the reasons to not opt into that, or basically always do that?
So I watched the WWDC talk, but it also wasn't quite clear to me. So when I created my new project in Xcode, I had to actually opt in to making my library mergeable, and also opt in to have Xcode automatically merge into my app. I don't know why it's not the default to put it on automatic and yes, mergeable. As far as I can tell, there are not really downsides. So your framework, it must be compiled with support for mergeable libraries in order to be mergeable, because Xcode will put extra metadata in there. So maybe it's not quite ready yet for some bigger apps, because I think apps like Booking.com or Uber, like huge apps with hundreds of dependencies, they will really benefit from this, because the dynamic linker needs to do way less work that way if all the libraries are merged in. yeah, I don't really have a good answer for your question. Anyone else? Okay, thank you.